Alright. Good afternoon, everyone. We're Team Greenberg, and we designed a pervious concrete-based airport fuel spill control system. It's a four-man team. Nick Kurzberg is our materials and concrete specialist and our technical writer. Ziad Saeed is our environmental and flow specialist. Ali Karim is our structural and geotechnical specialist. I'm Jamal John. I'm the technical drawing specialist. Our advisors were Dr. William Miller and Dr. Felix Udeo. So our abstract. Now we're motivated to do this project by a couple of things. Fuel spills are a major concern at airports. Because fuel is highly dangerous to the environment, and there are hazards that come about when you think about those things. In terms of fuel spills, seepage through concrete. If fuel gets into the water, it can be dangerous to your drinking supply. Fuel is also highly flammable, so it can explode. Now, our project contains the fuel in a safe and economical manner, and our goal is to increase the safety of the passengers and to also reduce delays. Now here, just kind of had to think about a couple things before we start designing our project. So, the strength of our concrete, we're going from here. The strength of our concrete is based off the load of the plane. So, depending on the load, we get the strength here. So, our mix also depends on the strength that we need here. So, using the strength in the mix, we begin our design. After design, we begin testing. We have to test for compression strength and permeability. And if those numbers are good, we can go right into competition and implementation. But if they're bad, they have to go through the system again and until we get the numbers that we need. Also, for our pipe design, we needed materials that were not also strong enough for our design, but also environmentally friendly. And we needed the pipes to be big enough to handle the flow that was coming through our system. Now, functional constraints. The concrete properties, our concrete had a compressive strength of 4,400 psi, and we need to be able to handle a 1.65 inches cubed per second flow. The slope also, the slope of the whole medium of our system, where the pervious, the thing that we have there on the bottom, the slope is 5%, and also we have 1% slope for our pipes. Our whole pipe system is 100 feet, and that covers, that's 1 by 100, so it's a 1% slope. Location of the airport terminals, they vary in size. Airports vary, the airplanes, but specifically at Terminal F, which where we're going to implement our project, the airport maximum capacity is 53,000 pounds. Now, the storage of the fuel, our fuel tank will, be able to manage the maximum amount of oil in a truck, which is about 2,000 gallons. And we'll also have room for, runoff and rainwater. Also, our concrete slab will be 25 by 50 feet with a 12-inch thickness. Non-functional constraints set by the engineering department. We had $500 to use, and most of our $500 went to the $368 oil water separator. Sustainability, our stress ratio needed to be below 0.55. And also our fuel interaction with the environment. The kerosene has a fairly high evaporation rate, but our concrete covers that. We also needed to make sure that our permeability rate was higher than our evaporation rate to make sure that we were covering all the aspects of the fluid. Follow the FAA guidelines. In construction, we just used materials that are available to us, and we got in the lab when we could. Sometimes that was time restricted. There were a lot of risks that we ran into designing this project. Evaporation, seepage, and absorption, like I said before. If fuel gets into the environment, it becomes very dangerous on many levels. So we look to avoid that. Debris, the airport's outside. There's going to be leaves, dirt. So it's not easy to keep it completely clean. But we also had a method here that could prescribe to the airports that maybe the people that work there that clean the grounds, maybe they hose down the concrete and use vacuum pumps to clear the fuel. So to make sure that our concrete isn't clogged up. Here it is. This is basically it right here. The concrete here, as you can see, is this tray. It's 50 by 25, and this is the first concrete layer. It's the 12 inches here. Below the concrete is the aggregate, which where the liquid will run through, and that's the 5-degree slope. It all meets right here at the orifice, the beginning of our pipe system, and the orifice runs the whole length of the concrete. And after it goes through the orifice, it comes out and the pipe goes down. It's 100 feet at that 1 degree slope, so that's a 1 foot drop right there. And that goes into our oil water separator, where the oil is separated from the water. There's basic numbers for the weights of the things that we use for our project. We got a total unit weight of 2,185.2, which is a little lower than the average, which is around 2,400. But we had to take into consideration the amount of air holes that we have for the permeability, so we lose some type of weight. Based upon the AC ratio and the water content, the AC ratio needed to be between about 4 or 5, and the water content around 30%. So based off those numbers, we get a permeability of 27.04 centimeters cubed per second, which is fairly good for the goals that we needed. Here is a current picture of Terminal F at the Philadelphia Airport, and that's the average plane that's there. What's highlighted is where the fuel, that's where they inject the fuel into the plane, and oftentimes it spills. There may be a little spill here and there, but the fuel just sits on the concrete. It doesn't really go anywhere. That can be hazardous also. Now, to design the slab, we had to use the 53,000 maximum takeoff weight there. We also used the 150 PCI for our K, our spring value for the soil, which is the average found around that area at the Philadelphia Airport. Now, to find our working stress, we used the modulus of rupture over the safety factor. And finding our modulus of rupture, we used our K prime, which is 8, which is the usual number at airports, and we multiplied that by the square root of our compressor strength, which is 4,400, and we got 530.66. Now, we knew that our safety factor had to be between 1.7 and 2, so we're looking to get a number in that range. But to find that, oh, no, that's not it. So to find a number here, we needed to make sure that we had satisfied our 2 numbers here. We also know that our stress ratio has to be 0.5. So in order to find the stress, we use the stress ratio and our modulus of rupture, which we calculated, and we get minimum strength of 292 psi. So we use that strength, we use a 300, which is a little greater than 292 to give or take for certain things, and we get a safety factor of 1.77, which is between 1.7 and 2. So that works out. Here's just a graph of the numbers. We start here at the 300 is our fluxural strength. We go horizontally till we run into our 53,000 pound gear load. Back up vertically to our K. Oops, switched it up. 150. So that's between 100 and 200. Back horizontally to the 12-inch thickness of our pavement. Now for our pipe system, we use PVC pipes because they have really good physical properties. They're really strong, and the flammability characteristics are pretty good, and the walls are pretty thick. So we calculated that we need a minimum of 45 perforations to get the flow rate that we needed. So what we did is we used 2 sets. We used 2 sets of perforations here, 90 degrees apart, and 3 inches from center to center. Now, calculating our flow rate, we needed our outflow rate, the flow rate of our water, to be greater than the inflow that the pipe was going to handle. So we used a number of equations, Bernoulli's, the Darcy-Weisbach equation, and calculating our velocity for the water here, we use a number of heights. Now we start at 1 because that's the height of the total pipe system. You know, we have the 100-foot pipe at the 1 degree slope, at the 1% slope, so that's 1 foot height. So we're beginning at the 1 that's already covered. And then we go from every height up there, 1.5, 2, 2.5, 3, and 3.5, and that's the height of the aggregate. So that's the maximum the water will reach in the whole system. So we're basically at the very most that it can handle. But to get these numbers, we have to find our F here. Now to find F, we use Moody's diagram. And you have to end up over here. But we begin with our Reynolds number, which we calculate using the VD over V equation, and we get 6 times 10 to the 6th power, and we go up to our relative roughness, which we find to be 0.00005. Back over to the left, and we find out our F is 0.014. Now, we plug our F back into the equation. And we get that a velocity of 4.07 feet per second. Multiply that by the area, which is 0.785, and we get a flow rate of 3.9 feet cubed per second. Boom. So we have a flow rate that we need to satisfy. Now we need to make sure that our orifice can handle all the flow. So we calculate our flow rate for our orifice. We use our CD and our A, which is our coefficient of our drag in our area, and we find that with approximately 45 perforations, we can handle 3.34 feet cubed per second, which is higher than the 3.19. So we've met our goals. This is just to describe the relationship between the two. Now, the Q in, the flow in the perforation is strictly the flow of the system into the pipe system. The flow into the beginning of the pipe. So we start at 0 from where the pipe begins before it flows down to the ore water separator. And so we get from every height. That's the flow. So this is all the water that would be in the aggregate. Now the Q in the drainage area is the water in the aggregate plus the water flowing down through the pipe. So we begin at 1 again to come up to that 1 foot height of the pipe system. And you can see here clearly that the Q in the perforation, which is the flow from the aggregate into the pipe system, will always be higher than the Q in the drainage area. And this is just a chart to describe the numbers, basically to solidify our calculations. Down here is the flow rate, and this is the head, the height, and the blue. This line is the Bernoulli's equation, is the flow, and this is our orifice flow, what our orifice can handle. So as you can see, no matter how far it goes, the flow rate of our orifice of what it can handle is always going to be higher than Bernoulli's equation. So we're set. But there will never be an overflow, so that's great. Now, for our concrete, we had a test. We had many tests actually. For our 7th-day test, we got a mean strength of 3,086.67 psi. So we use that number to calculate what our expected strength on the 28th day would be, which is 4,387.48. And we're looking for 4,400, so that's around it. So, I mean, that'd be pretty good. But when we actually did it on the 28th day, we got a mean of 4,570.6 psi, which is even greater than what we needed. So that worked out for us. Now, well, this is great pouring technique. Just want to point that out. That's great. Permeability aggregate here. So we're testing for the permeability of our aggregate. So we need to find our K, which is our hydraulic conductivity, which is basically how much water flows through a material. So we find our K to be 0.66, which is good. Now, testing for absorption. This was also important because we wanted to make sure that things were getting absorbed in our system. We want to make sure that everything flows through and finds its way into the ore water separator. So we didn't want anything to be absorbed in the aggregate, like the fuel or the water, to possibly have it go into the soil or go into the air. So we didn't want to avoid as much evaporation or absorption as possible. So for our concrete, we get a 5.6% absorption rate, and for our aggregate, we get 2.2%. And those are fairly low percentages, so we're good on the absorption part. Now, we had to test the system. Once you make a system and it doesn't work, we've done all that work for nothing. So we had to test the whole system to make sure that the water that ran through our system was, drinkable and usable. So what we did here is we used 2 liters of tap water mixed with about 300 milliliters of alcoholic solution, which is basically rubbing alcohol. And so we found that the pH of the tap water is 6.5. The pH of the isopropyl, which is the alcohol, is 5.0. And we even mixed both of them and found the pH of that, which is 5.5. And then after running our fluid through our whole system, we get 6.5 pH for our filtered water, which is the same as tap water, which means you can drink that boy. You can drink that. If you drink, I don't drink tap water, but if you want to drink that, you can drink it. So it's drinkable. Also, the testing is based off density. So we had to use something that was very similar to kerosene, which is the main component of the fuel at the airports. So I mean, this 0.7, this 0.8, right around there. So pretty good. That's basically, this is our prototype here. As you can see, nice frame. That's oak wood, soil. That's the concrete. So basically, we wanted to see how much water we lose through the system, what we're losing, what we're gaining, and we ran a number of tests, and we got an average of 92.8% is what we retained from running it through the system. So that's a fairly high percentage. I mean, the 7.2% can be due to water that's left over, or it could be the minimum absorption of the aggregate or even the concrete. References. It's a lot. Questions?
Questions? Can you help me understand something a little bit? When you were talking about the safety factor and modulus of rupture, is that
Right.
Can you pull that up and just explain that a little bit?
I can do that. I can certainly do that. That's it? No, that's not it. This is it. Right.
Well, I guess what is spring value? What does that mean?
The spring value, that's how much spring of the soil.
Explain, I don't understand that. What do you mean?
It's like the compactness of the soil. Like, soil's compact or it's loose.
So it's got a value of 150, what's PSI? It's pounds per cubic inch?
Yes, PCI, pounds per cubic inch.
So I don't understand how that relates to springiness or flexibility or compaction.
It's the pounds per cubic inch.
Which
Like,
is how much pressure it can withstand
of
without.
course.
Okay.
Yeah.
So you've got your working stress,
Mhm.
which is the modulus of rupture over the safety factor.
Right.
You calculate a modulus of rupture as what's K prime?
Spring value is the prime. That's the 8. The 8 that we use.
What does that, I don't know, what's the definition of K prime?
It's the prime of the spring value.
So how do you go from 150 to 8?
Because that's the number that we had used for the equation.
Okay, do you know where that number came from?
Yeah, that's the number that's found at most airports. We found it in the book. It's in the references.
So you got your modulus of rupture,
Mm-hmm.
and you decided that the 0.55, what is that value again?
That's the our stress ratio can't be any lower than 0.55. It's one of our
So
constraints.
I guess this is what I'm confusing on.
Right.
You say the stress ratio, it says working stress sigma is equal to MR over SF.
Yeah.
And then you say sigma over 530 has to be less than 0.55.
No, that's the ratio.
Right, so is sigma in the second equation the same as the working stress up here? Is that sigma right there?
Right here.
Right. Is that the same as the sigma above? Right there.
No, this is just a stress that we're looking. This is the stress that we want to use for our quote for the world. Oh yeah, I mean, it's just an average stress number that we get. See how we get 292 and then we use 300.
I understand the math. I don't
Yeah.
understand the basis for the math.
You gotta use that to give it.
Other questions?
All right.
All right. Thank you.
Yeah.